Okay, so as I've been saying, this is brand new material, but really it references stuff that you already know. In a lot of ways, we're just putting it in a new context. We're just understanding more deeply about something you've already been doing, okay? Putting it in more formal algebraic language and context and understanding, and really making that bridge to college algebra. Okay? So this is section 8.2, and this is all about functions, relations and functions. Okay? And this is foundational in algebra, working with functions and different function families. Okay? And all their equations and their related to variable graphs and what those graphs describe. So our focus is going to be on linear functions, but we're going to sort of understand functions in general and be aware of other families and things that you'll be looking at more extensively in college algebra. So starting off with the basic definitions, a relation is just a relationship. It is a relationship between, I'm going to abbreviate here, BTW, a relationship between sets of data. Now, data can be anything. It can be numbers, letters, it can be words, okay? It's just information, okay, conveyed in some way. And if you create a relationship between data, saying, hey, here's something in this first set of data, and it's related to this thing in this other set of data, you've created a relationship. You've got a relationship. Okay? And this relationship between, and specifically, two sets of data, it generates ordered pairs. Now we're going to look at a couple wordy ones first, but in general we think of an ordered pair, order matters, hence the ordered pair, not just pair, of we've got an x value, always comes first, comma, a y value, and that ordered pair locks them together. They have a relationship. Okay? Hence a relation. Okay? And when you have a relation itself has some sort of rule or correspondence that glues x's to y's and creates that relationship. Now, a function is just a special kind of relation. So not every relation is a function, but there are some special relations that are functions. Okay? So every function is a relation, but not every relation is a function. A function is specifically a well-behaved, this is for the polite mathematicians among us, a well-behaved relation. You can take it out in public. Well-behaved relation. And what that means is each x, or first value, okay, each of the first value, each of the first set, each x has only and exactly one y. So basically, if you plug an x into your rule, you always know what y you're going to get. If you push that Coke button on the machine, you're going to get a Coke. Okay? You're not going to push it one day and get a Coke and the next day get a Sprite. Okay? That would be a machine that is not functioning. Okay? With a function, you know what to expect. An x will always produce one y. Okay? No choices there. Okay? So it, specifically, another way of thinking about that is there are no repeated x values. So if you have a relation that contains some ordered pairs, you will only see an x value used one time in any of those pairs. No other ordered pair in that relation is going to have the same x value. Okay? No repeated, but however, repeated y values are fine. Repeated y values are okay. Okay? That's not a problem. Okay? So I could plug in a 3, and I know when I plug in a 3, I'm always going to get a 5. Okay? It's never going to come out 8 or negative 2. If I plug in a 3, I'm going to get a 5. But if I plug in a 1, I might also get a 3. That's not a problem. Okay? It's like having more than one Coke button on the machine. Okay? That's okay. Or no, that would be more repeated X value. Scratch that. Sometimes I get that analogy backwards. So, all right, so let's look what that looks like in some real-world situations. Okay? So these first ones are kind of wordy relations, and then we're going to really bring it down to math and specifically to our linear functions. All right, so what we've got here is our two sets. We've got a first set, sometimes referred to as the input, and a second set, the output. Okay? And the set has elements or members. Okay? The members of this first set, the input, are people in a certain city. So how many elements are in this set? How many members? How many?
One.
Only one person lives in the city? Yeah.
There's only like people.
Yeah. Well, there wouldn't be infinite either in one city. That would take quite the population explosion. But that's why, I mean, in a sense, we don't know. Yeah. I mean, because it depends on the city. Okay. So there are a countable number of people in this city, whatever it is. Okay? I'm not sure which city it is or how many it has, but there's a countable number. Okay? And then we've got the elements here. Now, the thing that glues them together is the rule, also known as the correspondence. And in this case, the rule is each person's age. So if you pick a person from this input, which is the list of all the people in that city, however many it is, and you ask them, what's your age, to the nearest year, no fractions or decimals, then the answer they give you is going to be part of this second set, the output. And what defines this second set, non-negative, obviously, because you can't be a negative age, and integers, because it's said to the nearest year. We're not doing fractions of a year. All right, so that glues it together. So when we write our relation, and there's actually an infinite number of non-negative integers, but there's, in reality, what's probably the biggest one we would use that follows this rule. What's the biggest? This is technically infinite. Yeah. Non-negative integers, you can count until infinity. But is that the reality according to this rule? What's probably the biggest one we would use? 96. Yeah. Definitely not more than like 100 and, I don't know, the oldest person maybe 120. Yeah. Unlikely though, probably somewhere in the 90s. Yeah. Mostly. So when we write this relation, we expect that input, apply the rule, and get the output. Now, this relation, we're going to write it as, it's a relationship between sets of data. It generates ordered pairs. Now, there is a finite number of ordered pairs involved in this, finite because there's a finite number of people in a city. Okay? I say it's going to be a list of these ordered pairs by showing that brace. Okay? We're going to look at another way to show what, this is what's called a discrete relation. We're going to look at continuous ones where you can't use set notation. That's coming up. But for right now, these are countable. They're countable so we can list them. So this relation is a list of ordered pairs that were generated by this rule. So let's say Anna lives in this town, and Anna is 34. Input, output, ordered pair. Okay. And let's say Bob also lives in this town, and he's 65. And Clara is 7. Now, we got a lot of people in this town. I can keep going. Let's say we got Davos. Can Davos also be 34?
Yeah.
Sure. You got people in a town that are the same age. And so forth. I'll just dot, 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 however many people in the town, and then I close my set. So yeah, more than one person can be the same age, certainly. You're going to have in one town lots of people who are the same age. Am I going to have any other Annas?
Yeah. Not the same Anna, but...
Right, definitely people with the same name, but unless we're cloning, it's not going to be the same Anna. Right. So in that sense, no, the name might be repeated, but the actual X value is not, because Anna is Anna, that Anna. Okay? So your input, once you ask Anna her age, that's it. Okay? She doesn't have a clone. Is this a function?
Yes.
Yeah, no repeated X values. You can expect when you ask Anna, that Anna, what's your age? She's going to say 34. She's not going to turn around tomorrow and say 62. So this is a function. It is a relation also, but it is specifically a very well-behaved relation, and so it's a function. Here we've got, now this input we can also often refer to as x, and that generated our y, and so this rule generated our ordered pairs. So look at this correspondence or rule here. Our input has how many elements?
3.
Yeah, this is very countable. This is countable too, but we don't know what that number is. This one you can see, 1, 2, 3. Okay. And the output, or our y, how many elements there?
As many as
Yeah, right. That is a knowable number. I don't know it specifically right now, but it's a countable, knowable number. Okay? And our rule, our correspondence is eye color. Okay? So we're starting off with the eye colors. There's more eye colors than that, but we're working with 3 of them. Okay? So if I go into this room, I want to generate this relation, and I say, okay, brown eyes, raise your hand. How many people in Cincinnati are going to raise their hand? A lot, exactly. So I put brown eyes, and that might be, Ada raises her hand. Oh, but look, also, when I say brown, we've also got, Bill has brown eyes too. Probably a lot of people do. Oh, green, hey, there's, Carl. Blue, so on, Diana, and so on and so forth. And keep going until I finish asking all the people in Cincinnati. Or rather, I ask who has blue eyes, and when I say blue, that one, that one, that one, that one, green, so on and so forth. Okay. So this is a relation. I am gluing together 2 things that are related. Brown eyes matches with Ada. Brown also matches with Bill and probably thousands of other people in Cincinnati. Is this a function? No. It is a relation, because it relates, it generates ordered pairs, but it is not a function. Now the other examples as we slide forward, these are put in what's specifically called map form. These are maps. Okay? Again, more of a college algebra concept. You'll get into how you talk about functions, and mapping helps you see that relationship too. We have a correspondence. The correspondence is shown by these arrows. We don't necessarily know what the rule is. This first one makes sense. We're matching cities with their populations. Okay. Now, Lubbock, for example, maps to 206,000. Could there be other cities that map to that as well? Yeah, none in this input list, but there could be in the world. But none in this particular input list. Are there going to be other Lubbocks? No. I think there's somewhere in Eastern Europe that's named Lubbock. But it doesn't matter. Just like Anna's not a clone, it's not the same Lubbock. Right. So is this a function? Yeah. Each city can only appear once by its very nature. The y values, the populations might repeat, but it's still a well-behaved relation. I'm just going to use F for function now. Okay. Okay. Now we're getting more mathy with our numbers and letters. Okay. So let's look at how these relationships form. How many elements are in the input here?
3.
And how many elements are in the output?
3.
I see 3 in the box.
6.
But how many are actually used? 2. Yeah. So that's more specifically what we're going to define as what's called the range, that output. You see 3 in the box, but the only ones that are used are really what the output is, because nothing is going to output the 2, for example. So there's 3 elements here and 2 that are used here. So in this relation, how many members, how many elements are in the relation? That's asking how many ordered pairs are in the relation. Well, A goes to 3. Okay. Does A go to anything else? Okay. What about C? Also goes to 3. Okay. And nothing else. And E goes to 1. Any other ordered pairs generated? No. So this is an input that has three elements, and an output that has two elements, and the correspondence generates a relation with three elements. These elements are just single numbers or letters, and the elements of the relation are ordered pairs, three ordered pairs. Function or no?
Yes.
Yes, it is a function. 3 is repeated, doesn't matter. We know when we put in A, we're going to get 3, and that's what matters. A is not going to show up again. A doesn't go anywhere else. Okay, go ahead and write the relation to these two. And decide if they are a function or not. Make a note, how many elements in the input, how many elements in the output, how many elements, ordered pairs, elements of the relation. And then is it a function or not? One element in this input, 4 in the output. All 4 in the output are used, so it generates 4 ordered pairs in the relation. This one has 3 elements in the input, only 1 element in the output. There's 3 in the box, but only 1 is used, generating 3 ordered pairs in the relation. Which one of these is a function, the first or the second one? Yes, this one's a function. We know when we put in 1, we're going to get A, and that's it. No other surprises. But here, we put in 0, and we might get 2, and tomorrow we might get 5. So, not a function. Both relations, but one's a function, one's not. Okay. We're comfortable with that? Okay. All right. So, let's build on that. Okay, so as we've been talking about input and output, now we're going to define those a little more algebraically. Okay. So our domain is what we've been calling our input. Our range is what I've been calling the output. So the range is just the set. Now here's where we're going to expand it a little bit, because right now on this first page, we were working with what's called discrete or finite sets, okay? Meaning they're countable. This is a person, that's a city. There's no in-between things in that. It's point, okay? Countable, separate points. No dots are connected, okay? So now we're going to add not only dot, like we did on the first page, but the idea of connecting the dots and having that continuous relation or function as well. So the domain, when I define the domain is either the set or the interval. If it's points you can count, you use set notation with those braces, the mustache brackets. If it's continuous, where it's infinite, all these in-between numbers, you can't possibly list them all, then you need to use interval notation, because it has a starting point and an ending point, and it's all the stuff in between. And you use a different kind of notation to do that, because you want to say, here's the start, here's the beginning, here's the end, and it's everything in between. So you don't use the mustache brackets, the braces for that, you use interval notation. Now that should be reviewed from 308 also. I'll talk enough about it. We're going to do it especially a lot more at the end of the semester with inequalities, but it will be used in this context too for domain and range. So I'll be pointing out what you need to know about that as we go along, if that's not familiar to you. So it's the set or interval of all x values of a relation. It's whether it's a relation or a function. Still has, both of them have a domain and a range. And the output, the range, is the other thing, the set or interval of all y values of a relation. Interval. look at this first one. We've got 1, 2, 3, 4, 5, 6, 7, 8 points there. There are 8 elements or members of this relation. All this in between stuff doesn't count. Nobody connected the dots. It's point, 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 point. So if you were to write this relation, you would list 8 ordered pairs. There's no other, when I say relation or rule, well, you know, what's the correspondence, what's the rule? It's not as easy as eye color. Okay? There's not necessarily any meaning that you can say, write out what the rule is, but so you can just write the relation as the list of ordered pairs. So -4, 1, looks like 1 is y for all of them. -3, 1, -2, 1, and it's 8 of them. I'm running out of room, so I'm just going to do a dot, dot, dot to the last one, which is 3, 1, but there are 8 total. It's not infinite, there's 8. So in this relation, there's 8 elements. So the domain, as defined, is just the set or interval, and because these are just a list of numbers, it's a set with set notation. It's the set of all x values, okay, our input. So what is the domain of this relation?
-4 to 3.
Yeah. So you will have 8 elements here because there's 8 different x values. 0, 1, 2, 3. Notice when we list the domain, it's not ordered pairs. It's just the actual x values. The relation is a set of ordered pairs. The domain is individual x values.
So whenever we write down the domain and range, do you want us to like actually write down every single number, or just from like n to n?
We're mostly going to be working with the continuous ones. So yes, if I do something like this, I mean, it's not going to have really, you know, if I'm having you write it down, it's just going to have 3 or 4 elements, and it's just to show that you understand what the domain and range are. Yeah.
So yeah, write down.
Yes, write down everyone, because this implies it's infinite, and I'm not. That's why I specifically put as 8 elements.
Yeah.
I did this for safe space saving, yeah, rather than because it's technically okay.
Whenever I
Yeah.
wrote it down, I just did
Yeah.
-4 to 3, so I thought that would cover like basically.
Oh, yeah, when you do it for a test and all, you need to write the ordered pairs and be very precise, yeah. The range, what are the y values that are used? Yeah, just one. Our range is a single element set, one member, the number 1. Is this a function?
Yes.
Yeah, it is. There's no x value that's repeated. If you go to -2, you know that y is going to be 1. There's no other choice. So x will not be used again in another ordered pair. So yes. Okay. So this is the type. Now this word I'm about to share with you is not in the book. It's not in the homework. I'm not even going to test you specifically on this. What's important is I'm showing you the contrast so you'll be able to recognize and know when to use what kind of notation. Okay? Because right now all we've been using is set notation, and we're using that when we have what's called a discrete relation or function. Okay? And discrete, just sort of informally, so here's some other words what that means. It means it's finite, okay? Or countable. Even if it's a big number like the population of Cincinnati, that's still countable. It's not infinite. Okay? There are, there are specifically discrete points. It's just point, 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 point. Points, and they're not connected. The dots are not connected. So when you are working with a relation or function like that, you can actually list the ordered pairs, and you can list the x values, and you can list the y values. All the in-between numbers aren't there. So that's why we use set notation. And set notation uses the braces, the mustache brackets, and it is literally just a comma-separated list of the numbers, the specific numbers, the x's or y's, okay, or the ordered pairs. I'm abbreviating there if it's the relation. Okay? Whether you're doing the relation, which is a list of ordered pairs, or the domain or range, which is a list of numbers, it's in those braces to mean list, comma-separated list. This, this, and this, not the in-betweens. Now, technically, set notation is not an ordered notation. It's not an ordered list. So you are not required to put numbers in order in set notation. A lot of times it's easier for the eye to read, so it can be good form, but it's not required. It's not an ordered type of notation. Okay? So you won't be counted off if you don't put it in order. But like I said, it's not wrong to put it in order if you can, because then it's easier for the eye to read. Okay? Now in contrast, we've got this relation, which may be a function, and it's not just, I mean, you could name everywhere it crosses the grid, oh, the point -2, -3 is on here, and the point -1, -1 is on here, and the point 0, 1 is on here, and the point 1, 3 is on here. But if you just list the points you see, you're missing all those in-between points. How many points are on a line? Infinite. And not only, and even if there were endpoints here, it would still be infinite in between the endpoints. But on this one, it's not even endpoints, it's also arrows, so it's infinite even off the graph that we can't see. Okay? The dots were connected. You can't list all those ordered pairs. It's impossible. Okay? So we also then can't list the relation because we can't list all the ordered pairs. But we can maybe describe it by its rule. What is the rule of this? Exactly. It's the equation. The equation tells you, hey, plug in one x, it's going to spit out a y, plug in another x, spit out a y. That's the rule. It's the little function or relation machine that generates those ordered pairs that make this line and not a different line. Okay. So our rule, our relation/rule is y equals 2x plus 1. And that will generate infinite ordered pairs. So it describes our correspondence. Okay. Now I'm going to skip domain and range for a second and talk more about the type and the notation, so we can then describe that. So the type here, as opposed to discrete, which is point, 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 is continuous. Okay. And sort of informally, other ways of thinking that means it's infinite. Okay. It is not countable. Because you would just die before you finish counting it, because you'd never finish counting. So you can't, because of that, you can't list it, like in set notation. Okay? The dots are connected. So what we're using instead is called interval notation. And interval notation, I've used this before from 308, is with usually with inequalities. You solve an equation and you have a solution to the equation, one or two solutions depending on the equation. You solve an inequality and you're solving an inequality for a starting point, and the solution is everything from that starting point to infinity or negative infinity or in between 2 points. So you can't list it all. So inequalities use interval notation to say my solution is somewhere in this interval. This is where I start, and it's all the in-between numbers. Same thing for domain and range. We're going to use interval notation to say the smallest possible x value that we could have all the way to the biggest possible x value. Interval notation is very important. It's important. Parentheses are one of those things in math that mean something different depending on the context. So do not confuse the interval notation I'm about to use with what an ordered pair is, because it can look like an ordered pair, but it's not. It's a different context. Interval notation goes from smallest element, comma, biggest element. Or, that's with two parentheses, or you might have brackets, and I'm going to just abbreviate there from smallest to biggest. Or you might have a mix, one parenthesis and one bracket, or one bracket, one parenthesis. Huh? So, but when you have two parentheses, that's the one, don't confuse that with ordered pair. It's not an ordered pair. But order does matter in interval notation in a different way. Order matters. You're